Okay, it's 3 o'clock or 3:30. Let's get going. Welcome back from spring break. For those of you that are here, welcome. We have some new quotes in the month of March. First one from Winston Churchill. All great things are simple. Many can be expressed in a single word. Freedom, justice, honor, duty, mercy, and hope. That's a good saying. Here's our outline for today. We're going to hand back some homework. Conditions for equilibrium. We're going to be dipping into chapter 9 now, and we're going to start blazing. We got a lot of stuff to cover before the end of this month and into April. We're going to be talking about statics, chapter 9, which is about equilibrium. And then at the end of the lecture, I'll talk about homework 7. But before we do any of that stuff, UCF, go to March Madness. So that's good. I'm very happy. But does that basketball player, does he look happy or what? Man, I tell you what, that's good. I love seeing that. I'm very happy for those guys. They worked hard. All right. Now, I want to hand back some homework papers. Let me pause. All right, let's resume lecture. That's the part where I lecture and you guys listen. And you zip the lip. All right. Anyway, so I'm going to be handing back some more paper. I'm going to hand back a few every day. I won't be handing back all of them, but on one day. But every day I'll be doing some. Office hours tomorrow, 1 o'clock to 2 o'clock in the Physical Sciences building. Right in here, where the room 158 is. It's a big sunroom by the front entrance. And we can work on homework, just, if you can make it, and we'll work on homework. And homework 7 if you feel like it. And anything else you may want to talk about. Now, about the homework, etc., a couple comments. Homework 3, I just handed it back. And it's posted for everybody now in grades. All right. Now, I'm going to mention for the students that I just handed back, and I mention this for everyone, I highly suggest that you look at the solutions in the Talking PDFs section of our web courses area. And you may think, well, Dr. B, that was like exam 1 and, whatever. But, the final exam's coming up, and I may ask you a free body. There were some pretty poor free body diagrams, and I wrote a lot of comments on free body diagrams. Ready? Are you ready now? Yeah. All right. Because you're wasting everybody else's time. All right. So I highly recommend that you look up the solutions, as you should for all the homeworks. All right. Homework 5, the Bumblebee tilt test, that's also posted. Although not everybody submitted it, that was free money, but I don't know. Nobody's forced. Everything is voluntary at UCF, which if you think about it, this is kind of cool. It's, UCF, we're like a small city, right? 60,000 students. And everybody's here by their own volition. And what are we dedicated to? We're here to learn. We're here to discover that which is true. And it's all voluntary. That's a strength. That's not something you see everywhere. But we see it here. That's what college is. And it's an admirable thing if you think about it. Now, there's going to be more homework posted. I'll probably try to get some homework 4 posted tonight. And by the end of the week, hopefully Wednesday, I'll be able to give you guys some comments about the grade status of where we are right now. And of course, Wednesday, we'll submit homework 7, the space shuttle, gravitational potential energy levels homework. And I'll talk to you before we dismiss about that in specifics. Okay, questions about grades, and homework grades, and other stuff? Yes. A thing? You want me to make a thing about what's going to be on the test? Well, everything since the previous exam, so, whatever that happens to be. Just organize your notes. And look at the YouTubes, and I have, like on this page here, we're going to be talking about equilibrium. There's your tip. We're in chapter 9.2, or we're in chapter 9. That's figure 9.2. All right. So just go back over all the YouTubes and just organize your notes, and that's what we're going to be talking about since the last exam. All right. Question. Yeah, after homework 7. So homework 8 is going to be our first do-over opportunity. So that'll be after the exam and stuff like that. Okay. Question. And it looks like we'll have several opportunities to do that, so it's not going to be like highly pressurized. So we'll try to do something good, something that's helpful, because I know a lot of you guys are worried about your grades, and if you work hard, you can get a good grade. Okay, question. No, the Bumblebee tilt test is not up. That's oh wait a minute, wait a minute, that is up. That was homework 5, the pre-graded one. You didn't turn it in, I guess, on the test day. You didn't? You did? All right. Send me a message in web courses and I'll double check. Oh, you know what? Somebody in here I talked to on web courses over the holiday about a no-name homework assignment that I had and was ready to give back, but there was no name on it. So it may be in a separate file for that or something like that, for that one. Okay, additional questions about that kind of stuff? All right, let's keep going about conditions for equilibrium. Equilibrium, hopefully this makes sense to you. The condition for equilibrium, number 1 is that the net force is 0. Here's a picture of some guy standing on the ground, and an upward normal force from the ground, the rigidity of that surface, and the downward weight force. And notice where they put that red arrow for the weight force, right at his belly button, pretty much. Okay, and for us adults, your center of mass is pretty much at the level of wherever your belly button is. Okay, that's why your belly button is where it is, man. That's its center of mass. I mean, that's the most natural place to attach a belly button. So the free body diagram you can see right over there to the right. And this is about as simple as you can get. This is like my typical example, the can of Pepsi on the tabletop. Okay, 2 forces, one of them up, one of them down, and they balance. All right. Now this guy is in static equilibrium. He's not moving anywhere. It's also possible to have dynamic equilibrium. And an example of dynamic equilibrium, as you can read, and I want you to read chapter 9 thoroughly. I've started annotating it. Um, Dynamic equilibrium, for example, is and we've had this on an exam. I think we had a true false. A car out on Alafaya traveling at 40 miles an hour in a constant direction. Does it have any forces acting on it? Or what are the forces acting on it? And what are the conditions? What are the relationships of the forces acting on it? And so I think the question was, or the way that I phrased the true false is, you can say that there are forces acting on this, but they all balance. That would be dynamic equilibrium. It's moving, but the net force is zero. All right. So the forces acting on this guy they're vertical. They add up to zero. That's, in this case, they're both vertical. But you can figure out various other. Let me go back. Do this again. You can figure out various other systems where you have, a lot of forces acting on it, and it's in equilibrium. Okay, so now I'm going to point something out. If you bounce a basketball off this guy's head, you can still knock him on his keister, all right, if he's not alert. And that means that you can tip him over. He's going to rotate clockwise and come to rest on the ground in a new static equilibrium. He's lying flat on his back or flat on his you-know-what. And that's what I want to talk about now. There's a second condition for equilibrium, and that is that there's no torque acting. Now, here's an example, another diagram from chapter 9. This is a hockey stick, right? All right, and in this situation here, check your free body diagram. You have two forces acting on the two red arrows. And one's coming in from the right, one's coming in from the left, and they're acting at the same point. They're in opposite. So this is like you holding on to a hockey stick, putting the squeeze on it with the left hand and the right hand. Okay? The hockey stick, you could be able to hold it up, and it won't be going anywhere. Okay? Now that's equilibrium. The net force is zero. Now, here's the counterexample to that. If you adjust the placement of those two forces, where the forces are applied on the hockey stick, it's an extended object, so you can put the force wherever you want. So if you put one force up high, forcing to the right, and one down low, forcing to the left, what's going to happen to that thing? It's going to spin. It's going to start to spin anyways. All right, so you're going to accelerate it not from point A to point B, but in a rotational manner. Okay, you're going to change its angular velocity state. In fact, the angular velocity state, let me get my cursor over here. The angular velocity state in this first one is zip zap. It's not spinning. All right, but here, this one's going to start to spin clockwise if you change where you apply the forces. All right. Now the free body diagram, the net force on this baby is still zero. So it's not going to go to the left or to the right. It's just going to stand in place and spin. All right. If these are the only forces on it. So the net force is zero, but you're still accelerating almost every gram of that hockey stick. But you're doing it in an angular manner. So we're changing the angular momentum state. Now, let me pause the podcast. I want to animate this a little differently. Hold on a second, students. Okay. Now the concept, the rotational analog to net force is net torque, T-O-R-Q-U-E. So that's a vocabulary term for us. And it's the rotational analog of force being the dynamical concept that changes the linear momentum, the point A to point B momentum. torque is the rotational analog of that, in that it changes not the point A to point B linear momentum, but the spinning or angular momentum of an object. Okay, so torque defined in chapter 9.2, figure 1, the caption, torque is the turning or twisting effectiveness of a force. So those two forces, in the previous diagram, if they're head to head, they don't turn jack with that hockey stick. But if you dip them upward and downward, yeah, you're going to start to get that thing to spin. And that's a torque. That means you have some leverage. Go ahead and write down that word too, leverage. Leverage and torque, they're not exactly synonymous, but they're almost synonymous. Leverage is not, I don't know of a definition of leverage. It's more of an informal term. But when you have some net torque, you've got some leverage on something. You can make it spin. All right. Now, a couple factors involved physically with that. First is how many newtons you apply. So over here in these first two sub-diagrams, the red F vector for the top right, let me get my cursor over here. All right, so this is sub-figure A. You got a lot of newtons in this force vector, and this one's called F prime down here. And it's a smaller force. It's aimed in the same direction, and it's aimed at the same, it's applied at the same point. But the second one is smaller, so it won't open this door on the hinge as well as the big one in sub-diagram A. Right, so the number of newtons that you apply. So that's like saying, if you've got, if you're trying to open one of these, like a big door to the vault at a bank, they're massive pieces of steel on hinges, right? And you need a lot of newtons to even get it to close, right? But a little shrimpy first grader could not do it. They'd be there pushing for an hour trying to get it to move. Whereas us guys, we're adults, we got a lot more muscles, we could do it. And that's sub-figure A. Now, the second concept that affects this is where you apply the force. All right, so now that's encapsulated in the first two, and also C. If you dip the force down halfway toward the hinge, these guys are almost out at the doorknob, A and B. But sub-diagram C is pretty much halfway between the doorknob and the hinge. All right, now you'll be able to open the door there, but it won't be blazing. I mean, it's going to kind of ease open. And sometimes that's what you have to do if you can't reach all the way out to where the doorknob is. All right, so yeah, you got this situation of where you apply the force, especially where in relation to the location of the spin axis. Now, for a door, the spin axis is set. For something that's floating out in space, it's not attached to anything, it'll spin. It'll normally spin about its center of mass. So if you have like anything out in space, a satellite, and you apply some newtons at the top of the satellite, it'll spin away from you, and the bottom will spin up towards you, and the center of the spin will be right through the center of mass, wherever that happens to be. In a satellite, the center of mass is kind of hard to see. I mean, for us, the center of mass is easy to see, just, waist high, belly button high. So, here's another, if you think about it, if you're out in space, some of you may become astronauts, doctors in space. And if you ever have to go out in an emergency, like aliens invading or the space station or whatnot, and you get into your suit and you go out there and you get pushed, by Dr. Evil or, somebody that's also out there in a spacesuit, and he pushes you in the shoulder, Danny, you're going to go spinning, and the spin axis is going to be basically right through your belly button. Probably, depending on the spacesuit. But I mean, the spacesuit, I'm assuming, is pretty close to uniform distribution. So you're going to go spinning. You know what else would be interesting? To see what, like in the early Apollo and Gemini and Mercury, well, Mercury didn't have it, but Gemini, they had spacewalks, and those guys were attached to the capsule by an umbilical cord. In other words, a power cable and an air cable so that they could breathe. They couldn't go very far out of the capsule. And I bet if you look at some of those old-timey pictures, they're connected right at about belly button high, center of mass. All right, so where you apply it, whether it's at this, if you apply, and here's another, you can write this down. If you're out in space in a spacesuit and somebody gives you a sock right in the kisser, or no, not in the kisser, but right in the bread basket, right in your labanza, and right in your gut. And if they give you a shot right in the belly button, you're not going to spin. You're just going to go off in the direction of that punch. All right. So where it is applied has an effect. Now, the other thing that has an effect is at what angle do you apply the force? And that's encapsulated in these last three diagrams, subdiagrams D, E, and F. So this top one on the right, subdiagram D, all right, you're applying it from the other side of the door. All right, so that's backwards relative to this first F. And as a matter of fact, they call that minus F. All right, so it's the opposite direction of this F in subdiagram A. So you're over here, so you close the door. All right. Now, if you're over here on this side of the door and you apply the same number of newtons, F, but you're at an angle theta, you'll open the door, but some of those newtons, if you think about it, some of those newtons are actually pointing toward the hinge. And any newtons that you apply directly at the hinge, you don't get any spin. That's like applying a force to the bread basket. All right. If you get a sock in the bread basket, you're out of space. You get a sock to the bread basket, right into your belly button. You're not going to spin. If you push some newtons toward the hinge, you're not going to spin the door. But if you're at an angle, then yeah, you're going to have some newtons perpendicular to the door. That's the key. Perpendicular to the door. Anything perpendicular to the door, the slightest newtons that you have perpendicular to the door, it'll open, one way or the other, clockwise or counterclockwise. Now down here, here's an example, subdiagram F in the bottom right, theta equals 0. This is you pulling the doorknob directly away from the hinge. Well, you could do it, and you know what that's like? That's like you pulling on the umbilical cord of the astronaut, reeling him back in. Come on back in. All right? He's going to move nice and easy toward you. And this thing, but he's not going to spin. This thing, no spin. All right, so the angle at which you apply it, where you apply it, and how many newtons you apply, those are the three things that can change the rotational state of a door, an astronaut out in space, or the other thing. Here's something that's interesting. And I don't know if you guys have ever seen this, but is it possible to cause little one-celled animals or little parts of a cell? What are the little parts of a cell called? Organelles? Yeah. Is it possible to cause them to spin? Either the reason I'm asking that, you know what else has spin to it, designed into it? DNA. DNA is a double helix. It's got that, it's built-in rotation. So for those of you that are heading towards medical activity, you may actually end up studying cells or molecules. Definitely molecules spin. They change their angular momentum all the time. And you won't get to study that until 2054. By the way, it's possible that I'm going to be teaching 2054 in the fall. So for those of you that want to avoid me next fall, you can just, I don't know, I've had some students, but they're still fussing around with the schedule, so I don't know for sure what's going to happen. Nobody ever knows. Now, the textbook mentions this other quantity called lever arm, and it's, go ahead and write this down. This is a technical term. That's what engineers call it. The textbook author calls it R perpendicular. This R, the distance from the hinge to where the force is applied. But notice this subdiagram E. R here is not directly along the door. All the other R's are directly parallel to the door. This one is not, because the force is not applied on subdiagram E. It's not applied perpendicularly to the door or parallel to the door. This one's parallel to the door. Everything else is perpendicular to the door except for E. It's applied at a distance R, but it's tilted at angle theta, so the effective leverage distance is R perpendicular, which in this diagram is R times sine theta. And that's called the lever arm. Now, here's a bigger diagram of that. All right, and I'm going to show you some other diagrams of the lever arm. So here's this hockey stick again, right? And we're just applying some newtons of force in these two examples. Now down here, we've got a nail nailed through it so that it can spin about this axis, right? So what you do is you draw. That's good. That's good. You got a question? Yeah, it's. Do you want to explain it? Oh, yeah. Right angles. Yeah, 90 degrees. Yeah, that's an easy one. Good. Good. You guys good? Yeah. Good. No, I don't. You know, I was. You know, I would love for you guys to explain something anytime you feel like you want to explain it. And I'm not being facetious. I'm not teasing you or anything. I would love to hear it. Anybody that has the guts to do it. It's good because it's a good challenge. Anyway, so what you do is you go to your point of application and you look at the direction of the force. Now this force is perpendicular to the upper part of the hockey stick, right? You draw a line in that same direction, all right? And then you go to the spin axis and you say to yourself, all right, I'm going to draw a line segment from the spin up to this line, wherever it is, and it's got to be perpendicular to the line. So if you're making this sketch, make sure that this is a perpendicular angle here, or as we say, 90 degrees, right? So this is 90 degrees here. And notice that this dotted line here, this one's labeled R, that's the distance from the spin axis out to the point of application. That's not your leverage distance. This is your leverage distance, your lever arm, R perpendicular, right here. Now over here, it basically shows you something different. All right. Now this one is it's a different spin axis. So you can spin something about any axis you want. All right. Now the natural axis is an axis going through the center of mass if it's unattached. But if you have a hinge, you have a hinge. You know, that's fixed. But if you have a hockey stick, you can nail a nail right through the top of the hockey stick, right? And it'll swing around this thing. Right? So you apply some newtons down here, it'll swing clockwise. Whereas this one down here in subdiagram A, this one's going counterclockwise, right? So so you go to your line of force, okay? Here's your force, same force, and here's the straight line. in that direction. And you don't really have to draw much because the straight line perpendicular to that one from the axis down to this line of action is pretty much parallel to the hockey stick for this spin axis. But see, for this one, no, it's not. Right? Now, here's another diagram, and I challenge you to make this part of your notes, but it's going to be in the YouTube, so it's just as good. Right? Now, this is this is not photoshopped. This is a real crescent wrench for big jobs. That's all I could say. And I've seen bigger ones. I mean, you go out to the oil fields out in Texas and whatnot, you'll see some monster tools out there, big wrenches. Anyway, so this guy's holding this wrench, right? So we're going to assume this is the pivot point. Okay, so make a note of that. Big crescent wrench. Now, here's his other hand, and we're going to assume he's exerting some force about like that. So there's your applied force. So F subscript app. Right? So go ahead and sketch that in. And, this is pretty much the point of contact, right? And the reason I have it slightly tilted is because it's going in the direction of his humerus and ulna. Now, for those of you that have not had anatomy class, that's your forearm, your two forearm bones. Right? So that's the direction so rub out that vector, or and I'm going to remove it and put in the line. This is the line along which the force is applied. All right. So now I want to get a line from the pivot up here down to this line. Right. And it's got to be perpendicular. And so that's pretty much what it is. All right. So this blue. So that's your R perpendicular. For this pivot and this particular application of force. Now, if you shorten up your grip and you change the direction, you could grab that wrench. It might not be very, you might not need a whole lot of leverage. Like a lot of times you're working on something and you break the nut loose, and then you can go in with your fingertips and just, loosen it up by hand the rest of the way. Right? Or just shorten up your grip and grip it here, and even change the direction. Change the angle of your forearm to the wrench. Yeah, and so that's kosher. You can do that. But if so, you'd have a different calculation. And as I've said before, Physics 2353 is right triangles everywhere. And if you think about this one, there's a right triangle here. The blue R perpendicular is a hypotenuse, a yellow base, and then the other altitude would be from the yellow line straight up the spine of the wrench back to the. Oh, wait a minute, that's not right. I'm looking at it from this angle, but let me look at it from this angle. Okay, so the hypotenuse would be the wrench from the white dot down to the hand. And then the two perpendicular sides would be R perpendicular, of course, and then the yellow line segment. From this point down here where they intersect up to about here, the middle of the wrench. So that would be a right triangle. All right, now here's the formula for the torque. It's whatever force you apply times R perpendicular. And it has units of meters times newtons, or Newton meters. Now let me ask you a mental IQ test question. And doggone it, I forgot to bring the clicking questions today. So you won't be able to show your brilliance. But I will ask you this mental IQ test question. What is a Newton meter also known as? Raise your hand. Yeah.
A joule.
That's right. A Newton meter is the same as a joule. Now, there's something mysterious about that. A Newton meter in this context is something that causes time evolution. you change the dynamical spin state of the wrench or whatever is being torqued. But normally, energy is not connected to the time evolution the same way. Like kinetic energy, it's not connected to time evolution the same way that torque is to the spin evolution. So it's something mysterious about the structure of space-time. Basically, the fact that in space, there's no change in the laws of physics if you make a translational change of position or if you make a rotational change of position. Those are two symmetries of space-time. So in other words, if you spin around backwards, or if you go to Australia, you don't, where the land of down under, you don't have to change the laws of physics down there just because you've changed your angular state with respect to the Earth. The stars look different, but the laws of physics are the same. So, but it's nobody understands why this is true. I don't think it's really a coincidence, but yeah, Newton meters, joules, and angular momentum. That's even more mysterious. All right, so this is a little introduction. Finish chapter 9 and start reading into chapter 10, but do not dismiss, because we want to talk about homework 7. All right. Homework 7, if you haven't started, first look at the mini lecture on YouTube. All right? I go into great detail about the space shuttle and the energy levels out in space. Then, of course, read the PDF and think. And when you're right, this is not a difficult problem as a calculation. But you may find it difficult as a conceptual thing to get a hold of. So that's why I say think. And when you've got your answer worked out, remember that you're writing a written problem to me. You're communicating. So I don't want to just see a bunch of numbers on the page. I want to see it there. It's simple enough. You can write a few sentences. Use carefully labeled diagram. You might not even want, you could make a diagram if you want. A picture of the Earth and the shuttle and stuff like that. But definitely remember it's a written communication to me. Now, along those lines, let me just remind you, if you feel like coming to office hours tomorrow, yeah, we'll crush it. 1 o'clock to 2 o'clock, room 158 in the physical sciences building right in here. This is the homework crush down party, all right, for 1 hour. And we'll just work it out together, half and 50-50. We'll just, everybody will do a little work. All right, now you're dismissed. I'll see you. If you want your homework 3, come on up here if you didn't get it earlier. Oh, it's due Wednesday. Dude, you got to read the thing. Yeah. What's that?
Due Wednesday.
Yeah, it's due Wednesday. Yeah.
So I'm just learning more about cars, and torque is playing a really big role in that. Longer the
they
piston
advertise
arm is,
that.
Yeah. I've learned that longer piston arms mean more horsepower. Does that mean that because there's a longer lever that it's rotating the
Because there's a certain, gram for gram of fuel, gasoline vapor, 1 gram of gasoline vapor will have a certain amount of delta P on the piston, right?
Exactly, yeah.
But, so that, and it happens in a certain set amount of time, right? So that's delta P over delta T. It's a force, right? But the lever arm, depending on the length of the piston arm, that means that you've got a different amount, even though you've got the same amount of force, you have different amount of torque.
Yeah, even though the combustion amount is the same for the
And,
cylinder,
and,
it's still.
yeah, so the torque, and then they have, got your camshaft and everything where everything, all 8 cylinders got a fire and, and they each do it an eighth of the work and everything, but
Yeah, it's cool.
yeah, it's very
It's all
cool.
clicking.
I should read up on, my big brother's an engineer up in Detroit for the automakers.
Yeah,
And
I feel like
he's all over this torque and stuff.
I think for cars the analog, at least for me, for that tools and like cars are like the really big analog that bring it all together.
Yeah.
Cool. Thanks,
All right.
Oxby.
You're welcome. Homework?
Yeah, this Wednesday.
Wait a minute, we have homework?
Yeah, it's due on Wednesday.
Oh, you mean the one that you're supposed to look at the YouTube first, and on the YouTube it says it's due on Wednesday? And in fact, I also put it in discussions that it's due on Wednesday. Actually, everything's being recorded here. I shouldn't mock you guys on the YouTube. Hold on a second.
Maybe I'm crazy or something.